this up and throw it on, put the TV camera on it later. And while that's heating up, I'd like to show you another one that we've got. Okay.
Houston, traffic check on your picture. How's it coming through to you now?
We're getting a pretty good picture, Ed. We're not noticing any difference in the crystals and the circular heat flow crystals there.
Over here we've got another. Well, let's take another one of the convection types. Let's take the metal castings there out. Okay, Al's now got the another experiment which we call metal composite. So we have 18 different samples. These samples are metal, and really what this experiment is to get some data. Okay, how's that picture now, Gordon? Can you see the metal composite experiment?
Yes, now it's settled and we're seeing it very well.
Okay, and what we have are 18 of these small canisters, each one containing a different metal and or a mixture. And the purpose of this experiment is to get some data on casting under our weightless or zero-G condition. And here again, when you cast metals, you heat them, and when they cool, you have convection currents in them. Hopefully here in our laboratory, we can heat these and cool them. It will have even cooling. And also another part of this experiment is some of the metals are mixed with fibers and our various other particles. And the theory here to increase the strength of the casting with these fibers. Now on Earth under a 1G field, this gets to be a rather difficult process because during the cooling, the fibers settle out and you don't get a homogeneous mix and a cooling, so you don't have equal strength. So what we do is we heat these up and then we run through various processes. Some of them we shake, some of them we don't shake, and then we cool them. We put them on a little heat sink here, and we'll let it set and cool for a certain period of time, and then we'll change it, put in another casting, and press ahead. There's really not much else to show on TV with this one. It takes quite a bit of time by the time we run through all the casting, but we just park it up in the tunnel out of the way, and when our kitchen timer goes off, why, we'll either cool it or put in a new casting and press ahead. And I see getting some action on the convection experiment over here on the radio experiment, and would be real curious, Gordon, if you could pick this up if you've got enough light.
Yes, Stu, we can see a difference, particularly in the, as we're looking at it, upper left quadrant of the radial window there.
Okay, now as I said before, this quadrangle will heat faster, so you'll see more of a faster color change. Now these two will also heat, and these are the two that really show our zero-G condition, because these two will and are heating out, extending the radial distance out at the same rate. So we're not getting any help on either one of them from the convection current. And the fourth one, it just now starts to pick up. And we'll drop off from that one and just let it extend out a little bit. We'll talk about another experiment we have that also deals with convection.
It's very apparent that the upper right and lower left quadrants are heating equally. It's a very good picture.
Okay, and we did run this experiment on the ground before flight, and it was a very marked difference. It's quite impressive how it's working.
You do understand that this quadrant down here is a higher temperature crystal. That's the reason that it's not going out as fast as the one in the upper left quadrant. It has nothing to do with the gravitational effect at all. It's a higher temperature crystal down here.
Roger, Al.
Okay, now, Gordon, our intrepid LMP is holding another experiment, and how's that picture look? Can you get anything of Ed in the blue box here?
We're not getting it yet. It looks like you're still getting the camera settled down. I'm seeing Ed. Now we're seeing Ed. That's right in the center now. I think maybe if you stop the lens down, the little window is overexposed with respect to the rest of the scene, so we're seeing just not much more than just a bright light. That's looking real good now. I think that's a good setting right there.
Okay, Gordon, and what we have here is an electrophoresis experiment. And we're not going to run this one on the TV camera. It's a one-shot operation. But on the left side here, we've got 3 channels going across this beauty. And over on the left in a chamber, we have 3 different compounds containing organic molecules. And what we're going to do is apply a voltage to each one of these chambers and then open up the partition between the chamber where the organic molecules are and our channel going across. And the theory here being that as you charge the molecules, they will move out across this channel. Now, some molecules will take a better charge than the other ones, and they'll move faster. Well, under a gravity field, here again you have the convection current, and it tends to mix up the molecules. The heavier molecules settle out to the bottom of the channel. They don't make it all the way across, and so forth. All the problems involved with the convection again. So here, hopefully the only variable will be the different type of molecule. And we hope these molecules will then separate themselves in bunches based on the assumption that all molecules of the same kind, are all been doing their physical conditioning and will run at the same rate. So anyway, the molecules will move across and hopefully we'll separate them into bands. Now, we've got 3 different types of molecules here, and the simplest one is just the red and blue dye. And this phenomenon will take place under a gravity field, and this happens on the Earth. And we work up in numbers up to quite heavy molecules. And these are the ones that we cannot do on Earth, and we're trying to see if it's possible to do them here under 0G, and there are quite a few ramifications to this if it really comes off. And one of the most obvious is in the field of medicine and making pure vaccines and so forth. Now, we don't expect this experiment to solve the problems. We're trying to get a hack to see if the theory is correct, and also to work out some of the engineering details, such as when you heat, apply this voltage, you form a few gas bubbles around it. And so we have to have a little pump that circulates the fluid at a very low rate, and we'll want to see if this works and if it disrupts the travel of the molecule. So this we hope is the first step toward bigger and better experiments and eventually a truly manufacturing process.
Ed, if you want to move on down to closer to that light for a few minutes, we'll put you on the camera. Maybe your family can see what you've got hanging all over your face. We couldn't talk in shaving this morning.
Or yesterday morning either.
You might open up the lens slightly if you're going to a less brightly lit object.
Are you trying to say today it's not very bright, Gordon?
I guess I won't comment on the interpretation there.
Okay.
I'm being conspired against. Since I'm being conspired against, I'll take the camera back.
Okay, we'll come back down off of one that does not deal with the convection principle, and that's the transfer of liquids. If I can get out of the way here. And is that showing up, Gordon?
That's pretty good for centering. Can we,
Okay, are we washing up?
that's looking pretty good. You might move the camera down slightly now. It's in the lower part of the screen. Okay, it's centered well. It was. Also, you might try a peek on the camera. It might improve the exposure. That was one suggestion from the back room here.
Okay.
You have peak, how's it now? Peak and F8.
I think that'll work. You might open it slightly, Ed. Open the f-stop slightly, and I think we'll have it.
Okay, what we've got, Gordon, is, of course, two tanks here. And these have no baffles whatsoever. And we tried to transfer the liquid from one end to the other one and then back again. And we ended up in about the condition that you see here, not being able to do much with it. And I've got me a handy-dandy pump, which I'm going to mount on here. And this experiment is, of course, slanted toward the large space station, refueling operations, transfer of fluids on a space station. Anytime you have a rather large, complex structure up here, why, you're going to have to be doing this type of operation. And it's a first look at what type of baffles and we need, and you'll see this on the other side. What I'd like to show you is the difficulty you have when you're trying to do it without without the aid of any baffle.
Stu, we see a couple large bubbles in each tank. Would you point out just which part there is the liquid and which part is the airspace? Over.
Okay, the white portion you see is the bubble, and you should be able to see a green fluid around the bubble. Can you see the green?
That's affirmative. We can see what the parts that you're pointing out there. The colors on our monitor here are not coming in true, but that shouldn't hurt the point of the experiment. Go ahead.
Okay, well now take the, yeah, okay. And we'll, Al's now working this pump. Okay, we can't even get the bubbles to change too much here. Yeah, okay, and about all okay, if you'll watch that, about all you can succeed in doing when you pump with the pump is making the large bubble in the center, and the fluid has a tendency to cling around to the outside edge due to the surface tension. Now, this surface tension is quite important, and that is what will make the baffles work, as you'll see on the other side. But right now, the only surface for the fluid to cling to is right around the edge of the tank, and sure enough, that's where it goes with the bubble in the center. It makes it very difficult, if not impossible, to work with.
Okay, that's very apparent from the picture we're seeing now.
Okay, and a little bit of the hardware here. We have a valve up here at the top that connects the two tanks through a tube here. Now, Ed, if you can get it down, and we've got a valve on the top of each tank here, in which the pump will either pump into this tank or suck from that tank into this tank, and the tubing here goes from these valves to a little hand-operated pump. So that's the engineering behind it, and of course, as you can see, the liquid just clings to the periphery of the tank due to the surface tension. We'll now switch the tank and show you the operation using some baffles.
And while you're switching, I'll put the camera on Al and let the world look at him. He did shave this morning. Didn't help a bit.
Okay. We can see that none of you looked worse for wear on the preceding 3 days' activities.
No, we feel great up here. Just great shape.
Still a reminder, if you still have the heat on the radial experiment, you might turn it off. It might be overheating by this time.
Well, you might swing on over. There's another part of the experiment that we're not sure you'll be able to see that we turned on instead. I don't know whether Ed can get on the camera or not up here at the top yet.
Okay, now up here we have down here, of course, where we're heating extending out radially from a point heater. Okay, up on the top we're heating. Stand by one here, we'll get the camera rigged up. Okay, we've now switched to the zone cells, as they're called, and here again we have the different crystals.
Ed, can you refocus there? As you moved in tight, we lost the focus and lost most of the detail of that part of the experiment.
How's that, Kurt?
Okay, that's better. I think that range is good. Just hold everything as it is.
Okay.
Okay, Gordon, now this is essentially the same principle, only a different type heating arrangement. Here we're heating with a band in the center, and we have the crystals in longitudinal strips. running out from the center, and I don't know if you pick up the color difference or not on these bands as they move out.
We can see a little bit of difference there. It's not readily apparent, but as you pointed out, I believe we can see those zones moving out.
Okay, and that's it. Basically now, when we actually do the experiment for data, we have a 16mm camera that sits out 1 foot, and we turn it on, and it takes the pictures, and you go through a sequence here. So it's a detailed experiment in which we have the procedures, and we run through those, and just what we're doing here is just showing you the growth features of the experiment and its typical operation. Not trying to show you exactly how we gather the data or anything like that. And we're turning off the heat convection experiment now.
Roger.
Okay, how are we focused on the tanks now, Gordon? Stand by.
Okay, Stu, that looks really good. Just center it up slightly, and we can see the liquid and the baffles very clearly. Over.
Okay, and just point out that we got 2 different type baffles. I think you can probably see the baffles on this side, and over on this side there's 2 baffles running up, and with a little different feed-in arrangement. I mean, bottom on the baffle. Okay, now I'll steady up the camera, and I will supply some power on the pump, and you'll see the liquid now moving out, and due to the surface tension on the baffles, it clings to the baffles and comes out and fills up the tank in an orderly fashion instead of going up the side walls and leaving that large bubble right in the center.
That's a beautiful demonstration. It's very clear from here.
Okay, good. Okay, we've got just about all we're going to get out of the tank. Now, Al will back it up, and we'll show you how the other set of baffles work. And you'll note the baffles not only aid on the fluid coming into the tank, but also it makes for a nice orderly discharge of the other tank. Now you can see it coming into this tank with, here again, surface tension on the side walls and the 2 baffles, and proceeding to fill the tank.
That's very clear, Stu. You may run it back once more.
Okay, we'll give it to you again. And I don't know if you can see it or not, Gordon, but when a bubble does come into the tank, it's broken up by the baffles and tends to hang in pretty well. There, we just saw one burst there, if you happen to notice that.
Hey, we can see that very clearly.
Why don't you run it fast? Show the slosh if you get it that fast.
Okay, we're going to increase the rate of flow here on this one.
Okay.
Okay, now with the faster flow rate, you don't quite have time for the bubbles to dissipate using the baffles, and we did pick up a few more bubbles. And Gordon, you really to appreciate this, you had to have tried the other side. I'm afraid that one didn't show up too well because all we had were the two bubbles in the center. But we proved to you the pump was working because it works on this side. But it was just impossible to transfer any fluid after we opened the valve the first time and got fluid out of one tank into the other one.
I think that's clear, Stu. Now that we see how well this side works, we can see that without the baffles, it's a pretty hopeless situation.
Raj. Okay, Gordon, that's probably about enough liquid transfer, and I think we pretty well covered the four experiments. Unless you've got some questions that I didn't make clear or has come up during the presentation.
One quick question: have you tried on the heat flow convection experiment, the flow pattern part of it, where you expected to see Bernard cells? Did that work out?
Yeah, we tried that, Gordon, and it didn't work out too good. Maybe while we've got the TV here, we'll talk about that one, and maybe you can get some help, and would like to try running it again. We ran everything except the Bernard cells. And Ed, could you put the camera back over on the convection experiment, Ed?
Yeah, what has been happening here in this particular experiment, we have a Krytox fluid that's supposed to come out of 3 different locations along the base of this cup. Can you see that cup from there, Gordo?
Yes, we're getting a very good view of it.
This is the outline of the cup right here. It has 3 very small holes down at the base of the cup at its periphery. And Krytox fluid flows in when we work a little hand pump here. And it's supposed to spread evenly over the bottom of this cup, which it does under 1G. The cup is a heating element, and we're going to study the rate of growth of and size of growth of Bernard cells in the Krytox fluid. Unfortunately, we're not sure whether we have air in the fluid, too much air in the fluid or not, but in attempting to get the fluid to flow on the base of the cup through surface tension, we find that we don't have any luck, and rather it comes up along the walls of the cup, adjacent to all 3 of the holes. And if you have any experts down there, we might talk about that a minute.
Have you tried to use an object to try to force the fluid to spread on over the surface by opening the lid on it and then trying to force it to spread out evenly?
You mean physically spreading the Krytox around, Gordon?
That's right. That's the question. I wondered if you'd tried that yet.
No, we didn't. Our instructions there said if it didn't adhere to the surface, we're to close up the lid and go home. We tried it 3 times, and to amplify there, it comes out of the hole, comes up the wall, and it spreads between the holes right on around the wall and just keeps packing up. We're most anxious to try it again, and we'll turn around on and try spreading it across there.
Okay, Stu, we don't intend to ask you to try all this on TV, but our only suggestion would be to maybe open it up and try to spread it across with your finger or with a tissue or something like that. But that seems to be the only idea to be offered.
Okay, well, if you've got the time, we'll turn on the Krytox here and let you watch it come out.
Okay, we'll be glad to watch.
What I'm doing here is opening a flow valve between the tank and Krytox and the liquid plate. And over here we have a pump, which is actuated when I turn it in a clockwise direction. And perhaps you can already see that we have fluid coming out right here. It's staying right in this crevice, moving up the side walls. Can you see that on the camera?
Yes, sir. We can see that very clearly.
See, it's doing it almost the same all the way around. This one is spreading a little further down the line, doesn't have quite as much fluid yet. But these two are spreading the same way. They're going up the walls as much as they're coming out on the floor. Now we'll get our finger in there and see what happens. I believe we may be able to get enough there to show you the formation of some of these Bernard cells.
Okay.
We have a thin layer here now. Let's turn on some heat and we'll see what happens.
Okay. Yeah, the comment for the cameraman there. We noticed a real improvement in the picture just about a minute or two ago, which if you did anything different there, remember what you did for future use.
Well, we just put it back on average from the peak we had it on a little while ago.
Okay.
Yeah, we should see some action here probably in a couple of minutes, Gordon. When these form, I think you saw them down at the Cape, did you, Gordon?
No, I didn't see those personally.
Okay, they're pretty impressive, and it breaks into the Bernard cell here.
I think we're having the formation of small cells, but of course the film we've put out here so far is fairly thin, and it's difficult to get the vertical circular pattern set up.
Roger. Stu, the experts here would like to pass along the fact that it should take longer to get the cell formation with a thin layer of fluid than with a thick layer.
Yeah, well, we have a peculiar pattern in this fluid, which you probably can't see. But the fluid which I put in the center stayed there, but there's a very thin layer here indicating that it's gone out radially again. And as you can see, we have some pretty good sized fillets that stay right on the outside of the cup. Very much the same principle of surface tension that you saw in the experiment of the tank without the baffles.
Roger, Al.
Well, the cells are forming. You can see very small cells, but you probably can't pick them up on the camera because the cells are only approximately 1/16 of an inch in diameter right now. I think, yeah, if you hold on just a minute, we're going to see some pretty spectacular formations. They're starting to form right now and get a little bit larger.
Okay.
Gordon, are you able to see the detail of the cells?
Not really now, Ed. We see some texture there in the fluid, but it's hard to say that they're really cells from here.
I think you'll be able to see them distinctly in a minute. They're starting to get larger and more active.
Okay, now we're seeing the cells pretty well. They're becoming much more apparent now.
Improved camera techniques again.
Al, do you recall how many total turns you've put on the knob that pumps the Krytox out? They're curious just what total quantity is in the cup at this time.
Well, we have about 2 turns full right now. Well, we do have some tiny cells here, and we'll play with this one some more and photograph it. In the meantime, you all might be thinking about that.
Roger, Al.
So we can definitely see these the formation of the same types of cells, although they're smaller than we had down there. Perhaps with more fluid in there, we could get larger cells.
Roger.
And Gordon, after the TV here, we'll put the camera back up and take a picture of what we've got here, just while it's there.
Roger, Tim.
Okay, I guess that's about all of it from our zero-G lab of Apollo 14. I think we're real pleased with the experiments, and I want to compliment all of the PIs and the work that they did. They came out extremely well. They went just as advertised on the procedures, gave us no trouble, and they've been real enjoyable to work with. And hopefully this is the beginning of bigger and better things in the way of manufacturing processes and so forth in space. And I believe Al has got some work here.
I just wanted to say a couple of words before we signed off tonight. What we've been talking about among the three of us as we've been setting up these experiments is the contribution this could make immediately and directly into American lives and the lives of people around the world. For example, if specifically these manufacturing processes of metals turn out to be better in the space environment, or the vaccines which are proposed to be developed in weightless conditions can be used effectively and immediately, and certainly this type of an operation in Skylab in the future can become immediately beneficial to the peoples of the United States and the peoples of the world. As a matter of fact, one of the things we were talking about in that connection was the tremendous achievements of the space program so far that have contributed particularly in the field of communication. For example, right now, I'm sure this broadcast is going directly overseas to millions of people who are seeing it in their homes through satellite. And I think many people have said that this improvement in communication through space satellites will certainly go a long way to solving the problems of the world, problems of understanding between peoples of different nations and different countries. We are reminded, however, as we look at that shimmering crescent tonight, which is the Earth, on our way back, that there still is fighting going on. The three of us all have acquaintances, friends, and even relatives in Vietnam. We are reminded that some of the people, some of the men who have gone to Vietnam have not returned, that are still being held there, listed as missing in action, or as prisoners of war. And it is our wish tonight that we can in some way contribute to our efforts through the space program to promote a better understanding of peace throughout the world and help to rectify these situations which still exist. And with that thought, for Ed and Stu and myself, I will say good night to you from Apollo 14.
Roger, Apollo 14. Thank you very much for the very interesting and thank you very much for the whole show. We've enjoyed every minute. Good night.
Inspiring was the word that Gordon was looking for.
Okay, thank you. We're ready to go anytime.
Okay, Al, the questions that you will be asked at this news conference have been submitted by newsmen here at the Manned Spacecraft Center who have been covering the flight.
Go ahead, Al.
Go ahead, Al.
Could you hold on just a minute? We'll get in position to answer the questions.
All right, fine. Just let us know when you're ready. And for your information, we're getting a very good picture.
Now?
That's affirmative. Good picture. All three of you in there. The questions that you will be asked at this news conference have been submitted by newsmen here at the Manned Spacecraft Center who have been covering the flight. Some of the questions they raise have been answered in your communications with Mission Control, but the public at large has not necessarily heard them. The questions are being read to you exactly as submitted by the newsmen and in an order specified by them. First of all, for Al and Ed. Cone Crater was your major objective on your second moonwalk. You almost made the rim. How close do you think you got? And do you believe you collected enough rocks and samples to accomplish the purpose of your mission?
I think so. Let me take the first part of it with respect to how close we got. I think we were within perhaps 100 yards or less of the rim, and certainly in a boulder field that was right there associated with the boulders in the rim. I agree with Al.
I agree with Al. I think we were within 100, 150 yards. I think the majority of the type rocks we would find at the rim or in the boulder field that we were working. And although it was a disappointment, just as a matter of challenge not to get up there, I think we accomplished the scientific objectives that we went for.
It is hard for us to get a feel for what it was like in the large boulder field. Was it a forest of big rocks higher than you? Could you see any distance? Over.
Well, the rocks that we were in were ranging of different sizes, but they ranged up to 10 or 12 feet in height above us, so at times we were behind rocks that were taller than we were. As far as the mobility is concerned, Ed, you want to talk about that?
Yes, we didn't have a great deal of trouble moving around the rocks. We didn't even have trouble moving the bet around the rocks, except we did have to dodge them, and of course have to be a bit more careful with the bet than walking without it. Our major problem, however, was the undulating terrain, where you simply couldn't see more than 100 or 150 yards away from you and see landmarks. Consequently, you were never quite sure what landmark would appear when you topped the next ridge, and we were very surprised when we topped the ridge, or approached the ridge, which we thought to be the rim of Cone Crater, to find there was another one beyond it. And that was the beginning of the real problem.
The next question is, tell us about your problems of fatigue, orientation, and visibility, and apply them, if you will, to the longer 7-hour moonwalks planned for Apollo 15.
Well, I guess we didn't realize that we had problems of fatigue and visibility. As far as we were concerned, our only problem was the amount of time allotted for the excursion. I don't know exactly what our heart rates were. Obviously, they were higher than the normal sitting rate, but we still were not operating at the maximum capacity of our backpacks for cooling, nor were we operating for extended periods of time at high heart rates. To us, it was just a matter of working against the clock. I think that we had the capability to go longer from the standpoint of fatigue. I don't believe that we were disoriented or lost at any time at all either.
Yeah, I agree with Al. If my previous answer misled you, it was to look around. We figured out where we were, but trying to do it rapidly made it difficult. And as Al says, time was our major factor. Given another 30 or 40 minutes, I think we could have reached the top of Cone Crater, covered all of our objectives, and been back in good fashion.
Well, let me add one thing here. I think if we had wanted to reach the top of the crater and do nothing else, that we could have done that within the time period allotted. But I think that the method in which we reverted to, that of collecting rocks from a point not quite near the top of the crater, provided a lot more geologically and gave us a better cross-section of the rocks in the area, and therefore a better chance of getting rocks ejected from Imbrium than had we gone to the crater and back and not collected as many rocks.
The next question is for Stu Russa. Stu, what did you see of the lunar module from orbit?
Okay, the first pass that I made on the landmark tracking, I picked the limb up with no problem. It just showed up as a white spot, obviously something foreign to the lunar surface reflecting light. But the ringer was the long shadow put out. The first day that I tracked it, why the sun angle was still pretty low, and you could see the shadow coming out, and the shadow and the reflection cinched it as the limb. Now you couldn't see a shape of the limb as such, but there was no doubt that the limb was there. And then on the next day, as I was doing landmark tracking, it was not in the schedule to track the limb again. However, I had a landmark just prior to the Frau Morrow region and one after it. And I was in the right attitude for landmark tracking, so I looked for the limb again, found it this time without any trouble. The shadow had diminished to almost nothing, or it's very small, but here again, then I could see the glint coming off the ALSJ, but this time the ALSJ had been deployed, so I could see the glint coming off it, and checked with Ron Evans later on and told him where I thought it was, and he agreed that was the ALSJ location.
The next question is also for you, Stu. A top priority for you was taking detailed pictures of the Descartes crater as a possible landing site for a later mission. Since your big camera was broken, do you think you got enough high-resolution photos?
Well, I guess, I'd say yes. We made 3 passes, and with the 500 millimeter, using what we call the COAS maneuver, or you pitch and keep the camera on the Descartes landing site, and this way you get a real good stereo. And I guess we'll have to develop the pictures and see how they are, but I'd say the answer to that's probably yes, but I really can't answer it completely at this time.
With your docking problem and battery problem, a board switch problem, and the problem with the landing radar, how concerned were you about not making a successful landing or a safe return?
This is Ed. I never doubted it for a minute we were going to make it.
Well, I guess we're always concerned about the operation of the equipment. That's what we're up here for, is to assure that it operates within the best of our abilities, and as well as it's designed to function all the time. We're always concerned about that, and we still are. We still have a little bit of this voyage left to go, and we're still concerned about a safe return. I think that anyone that's involved in this kind of a business of research flying has to be concerned until the flight is totally over. I'd like to make one other comment, too, about the question about the Stu's pictures of Descartes. The photographic technique which he used was essentially the same as Apollo 12 used, which took the pictures of the area in which we landed. And we feel that was successful.
The next question, other crews had trouble with dust. How did dust affect you on landing? on the surface and on the way back.
Well, let me take the landing part. We'll give Ed the surface part, and let Stu handle the way back part. As far as the landing was concerned, there was less dust than I'd figured, and I think that was generally borne out as we progressed through our EVA. But the dust started forming, I think, perhaps 100 feet above the surface, maybe 150. It was a thin layer, as we've seen before, but less dense than what I expected, and it did not interfere with my vision or capability to land at all. And you want to talk about how it was on the surface?
I think it was substantially as previous crews have reported it as far as working on the surface is concerned. It's a nuisance. The material is soft. It clings very readily to equipment, to your suits, and it's a nuisance. But surprisingly, we didn't find that we had too much of it in the limb with us in the evening, or rather the first night, nor do we felt we carried too much of it back in with us after the second EVA, except for the fact that it had impregnated the cloth of the suits and was on most other pieces of cloth. However, it came off of the metal very readily, and that didn't cause any problem. I think it was more of a nuisance than anything else.
Okay, as far as after the docking and on the way back, the dust problem has really been non-existent. They, of course, Al and Ed took their suits off in the limb, and then we have a vacuum cleaner in the command module in which I passed over, and they vacuumed the suits, and I passed over several bags in which they put all of the equipment that they brought from the lunar surface into these bags. They have zippers on them and so forth that are to keep the fine dust in. So I took each one of their suits and put it in a special suit bag that we have in here, and the other bags, as they came back across, and by holding a little positive pressure in the command module, we've had very, very little dust, and absolutely no problem at all.